A ring consists of a set R and two binary operations on R, which we denote usually by multiplication and addition. These binary operations should have certain properties in order for the triple R dot and plus to be a ring. The first of these properties is that the set R together with plus must form an abelian group. The second property is that R together with a dot must be a monoid. We are going to recall what these terms mean in a moment. The third property is that the multiplication must distribute over addition. What that means is that for every A, B, and C elements of R, A times B plus C must equal A times B plus A times C. And similarly, on the other side, A plus B times C must equal A times C plus B times C. Both of these equalities must hold for all A, B, and C in R. Now let us recall what it means to be an abelian group and what it means to be a monoid. R together with plus being an abelian group means that, firstly, the operation plus is associative. So A plus B plus C must equal A plus B plus C. This must hold for every A, B, and C in R. Secondly, there must be a special element 0 in R so that A plus 0 equals A, and that equals 0 plus A. With only these two conditions, R with a plus would have been a monoid, the concept we need for the second property of a ring. What makes a monoid an abelian group is that further, for every A, we have an element called the inverse of A, so that when I add that element to A, I get 0, and the same is true if I add them the other way around. These three properties that must hold for all A, B, C in the first case, for all A in the second case, and for all A in the third case, would make R with a plus a group. What makes a group an abelian group is an additional property that the addition is commutative. In other words, A plus B is always equal to B plus A. So that's what it means for R with a plus to be an abelian group. Note that the element 0 will always be unique. There will only be one element 0 satisfying these two equalities for every A. In a similar way, for every element A, there will always be exactly one minus A for which these two equalities hold. Now the second property, that R with a dot is a monoid, what that means is that firstly, multiplication is associative. In other words, A times B times C equals A times B times C for every A, B, and C elements of R. And secondly, that there is a special element, which in this case we denote by 1, such that A times 1 equals A, and that equals 1 times A. Once again, the element 1, when it exists, will be unique. So in other words, a ring is a mathematical structure consisting of three ingredients, R, dot, and plus, where R is a set, dot and plus are binary operations on R, such that these three properties hold. R with a plus is an abelian group, which means all of these properties hold for all values of A, B, and C, where in the second and the third case we require existence of a suitable element 0, which can later be proved to be unique, as well as existence of minus A for every A, which once again can later be proved to be unique for each A. Second property, that R with the binary operation dot is a monoid. That means that these two properties hold for all A, B, and C, as well as in the second case we ask for existence of an element, a special element, such that the equalities hold, but such element will necessarily be unique, as it can be shown. And finally, the third property, which expresses the idea that multiplication should distribute over addition. A times B plus C must equal A times B plus A times C, as well as A plus B times C must equal A times C plus B times C. Oh, we made a tiny error here. It should be times, not plus. And this must hold for all A, B, and C. Some mathematicians like to represent a ring by showing in the structure the special elements 0 and 1, as well as the operation of taking the inverse of an element. In this case, we would write dot, and next to it we would write 1, and afterwards addition, next to it 0, and next to it the unary operation for taking inverse. So some mathematicians would prefer to represent a ring not as a triple, but as sextuple of this form. Others might drop the minus and just point out the binary operations with the special elements. These are different styles of representing a ring. We can remove 0 and 1, which are called the additive identity and the multiplicative identity of the ring. We can remove them from the data because they are uniquely determined. It turns out that, as I said before, there cannot be two different ones having this property or two different zeros having that property, where in each case we ask the property to hold for all A. Because of this uniqueness of 1 and 0, and similarly of the unary operation of taking minus of an element of the ring, because of the uniqueness, we can drop these and simply represent a ring as a triple consisting of R, dot, and plus. Note, however, that neither plus nor dot can be dropped here. For a given operation dot, we might be able to find several different pluses that would make this into a ring. In each case, this would be a different ring. So having a ring means having specified not just a set, but also having specified specific operations dot and plus, making these axioms hold. A typical example of a ring is where the underlying set is the set of integers, and where dot and plus mean the usual thing of multiplication and addition of integers. In a similar way, we could consider the underlying set to be the set of all real numbers with the usual multiplication and addition of real numbers. We could also take the set to be integers modulo, let's say, 12. This is where we take all possible remainders you can get by dividing an integer by 12. There will be 12 of them, 0, 1, 2, 3, all the way up to 11. And then we can suitably define multiplication and addition in the usual way, except when the usual way gives an integer that's bigger than 11, we can then divide that by 12 and then take the remainder. That forms a ring as well. Another way of thinking about this ring is to think of elements of this set as equivalence classes for the equivalence relation that relates to integers when they are the same modulo 12. When we describe elements of this set as equivalence classes modulo n, we can then define multiplication and addition by using the following formulas. The equivalence class of A times the equivalence class of B is the equivalence class of A times B, where the times on the right-hand side represents the usual multiplication of numbers. Similarly, we can define addition using the usual addition of numbers. When we take this approach, we have to take care that the answer on the right-hand side does not depend on the representatives we picked from each equivalence class. You see, the equivalence class of A would contain many other numbers apart from A, and if we change A to, let's say, A prime, we won't be changing this object, but potentially this could have changed the answer, which wouldn't be correct, because the application of a binary operation should result in a unique answer once we have the same pair of inputs. This property is called the property of being well defined. One has to check that these formulas give a well-defined construction of dot and plus. After that, of course, one has to check also that the three axioms of a ring hold. In the case of the numbers, integers, let's say, and real numbers, where multiplication and addition was the usual multiplication and addition of numbers, it is fairly easy to get convinced that these axioms hold, as these properties are quite familiar properties of addition, multiplication, and the way they interact with each other through the laws of distributivity. Another interesting example of a ring can be obtained by taking the power set of a set X. Recall that power set is the set of all subsets of X, so elements of this ring will be subsets of X, where X is any given set. We can then take, in place of multiplication, the binary operation of intersection of subsets, while in place of addition, we can take the operation of symmetric difference. Recall that symmetric difference of two subsets, let's say A and B of X, is given by taking the union of A and B and subtracting from it the intersection of A and B. On the Venn diagram, we are selecting the parts of A and B that do not belong to the other one. It turns out that, indeed, with intersection for multiplication and symmetric difference for addition, we get a ring. The additive identity of this ring, the thing that will play the role of 0, will be the empty set. For if, let's say, B was the empty set, then there would be no overlap with A, so we would be left with just A, the shaded area A here, since the shaded area on the B side would be empty as well, and also the piece that was removed from A would be empty, since that would be the overlap of A and the empty set, which is empty. What about minus A? For a subset A, it's minus. What would that be? This should be an element so that the symmetric difference of A and minus a is the empty set. Basically what that means is that if I look at the diagram, it means that the shaded area must not exist at all. The only way this can happen is if both A and B are the same set. So in this case, minus A actually turns out to be equal to A, which is quite remarkable since this is a bit different to what we expect with numbers, where minus 5 would not be equal to 5, for example. Of course, the situation is different in this ring, where we do have some elements that exhibit the property that minus that element is the same element. For instance, if we take 5 here, 5 plus 5 would be 10. That would still be less than 12, and hence it would be a distinct element from 0. But if we took 6, 6 plus 6 is 12, and 12 modulo 12 is the same as 0. So 6, or rather the equivalence class of 6, would be an element of this ring that has the property that minus 6 is equal to 6. So we get rings out of sets as well. Once again, the underlying set of such rings is the set of subsets of a given set X, multiplication is intersection, and addition is the symmetric difference. Oh, by the way, what would be the multiplicative identity for such a ring? It would have to be something that when we intersect with A, we always get back exactly the same A. This has to be true for every A. As a consequence, we can conclude that the multiplicative identity must be the entire set X, the intersection of every A with the entire set X, because A is always a subset of X, will result in the same A. Now, certain rings are called fields. A field is a special kind of a ring. It has two additional properties to those listed as the axioms of a ring. The first one is that just like addition is commutative, also multiplication needs to be commutative. So for a field, we have an additional axiom that for every A and B in R, A times B must equal B times A. There is a further axiom that for every A in R, as soon as A is different from 0, it needs to have a multiplicative inverse. An element B must exist in R such that A times B equals 1. So for every A that's not 0, there must exist a B such that A times B's multiplicative identity. We formalize this idea by writing for every A in R, A not equal 0 implies that there exists B in R such that A times B equals 1. When a ring has these two additional properties, such a ring is called a field. Among the examples we considered, this one wouldn't be a field, since, for example, if I take number 2, an integer 2, it will not have the so-called multiplicative inverse. If I substitute 2 in the place of A, I won't be able to find another integer B such that 2 times B is 1. Of course, we know that 2 times 1 over 2 is 1, but 1 over 2 is not an integer. So this ring is not a field. What about this one? Well, we do know that every real number has a multiplicative inverse. For every real number R, its multiplicative inverse would be 1 over R. Of course, R can't be 0 in this case. But that's fine, because in our requirement, we are saying that the inverse, the multiplicative inverse, must exist whenever A isn't 0. In both cases, the multiplication is commutative also. Property number 4 holds, which confirms that this second ring is indeed a field. So this would be a field. What about integers modulo 12? Will that be a field? It turns out that it will not be a field. If we wanted that to be a field, this number, number 12, should have been a prime number. What about this ring? Is that ring a field? Well, it turns out that neither is this ring a field. Let's explain why these two rings are not fields. For this ring, the ring of integers modulo 12, note that 3 times 4, being 12, modulo 12 is 0. So in this ring, 3 times 4 is 0. If integers modulo 12 were a field, as 3 is not 0, 3 would have multiplicative inverse. There would be an element, let's say 1 over 3. Let's just formally denote it like that, which would multiply with 3 to give 1. But then if I multiply both sides of the equality above by 1 over 3, I would get, on the left-hand side, by associativity, I can group 1 over 3 and 3 together to get 1, the multiplicative identity. And on the right side, 0 times anything is always 0. This is something that can be proved in any ring, in fact. And then we will get that eventually, because 1 is a multiplicative identity, we would get that 4 equals 0, which is not true in integers modulo 12. This shows that 3 cannot have multiplicative inverse, and hence this ring cannot be a field. For a field requires that every element of the ring, as long as it's not 0, does have a multiplicative inverse. But let's get convinced that indeed, in a ring, x times 0 will always be equal to 0. We could write x times 0 as x times 0 plus 0, because 0 plus 0 is always 0. Then by distributivity, this is the same as x times 0 plus x times 0. Now we have x times 0 equals x times 0 plus x times 0. To both sides of the equality, we could add the inverse, the additive inverse of x times 0. On the left side, then, we'll get 0, because x times 0 plus its additive inverse will be 0. On the right-hand side, it will just cancel out one of the x times 0s. This would require use of associativity, since initially we would have this expression, and then by associativity, we would be able to shift the brackets to have x times 0 plus that thing, x times 0, plus its additive inverse, which of course gives 0. And then by using the fact that 0 is an additive identity, we get this equals x times 0. So we've proved that x times 0 equals 0 for every x, which is what we claimed here when we said that 1 over 3 times 0 must be equal to 0. Notice how properties like these are not explicitly mentioned in the axioms, but the axioms can be used to derive them. Now let's look, why can't this ring, where elements are subsets of a set, why can't that be a field? For that ring to be a field, if I pick an element A that's not 0, so any non-empty set A, it needs to have a multiplicative inverse. There must be a set B such that A times B would be equal to 1. But in this ring, what is 1? As we already said earlier, in that ring 1 is just the entire set X, whereas A times B is just the intersection of A and B. Of course, the intersection of A and B will always be smaller than A. So when I start with A, a subset of a set X, I will never be able to find another set that intersected with A, which would have given me a portion of A, would now result to be the entire set. Of course, If A was x, then we're fine. Then we could pick B to be x as well. But as soon as A is not x, it will not have a multiplicative inverse. So in this ring, only the identity element has a multiplicative inverse, the subset of x, the x itself. Whereas in this ring, we found one element, namely 3, that does not have multiplicative inverse. What about other elements? Some elements of this will actually indeed have a multiplicative inverse, and this will be exactly those elements whose GCD with 12 is 1. But this, of course, is not good enough, because for a ring to be a field, every element that's not 0 must have a multiplicative inverse. As long as there is one that doesn't have a multiplicative inverse, the ring cannot be a field. In the other case, we saw that almost nothing has multiplicative inverse except the identity element itself, which, in fact, in any ring will always have a multiplicative inverse, since we can always write 1 times 1 equal 1. So 1 will always be a multiplicative inverse of 1. But other than that, other than identity element for multiplication, in this case for intersection, which for any ring is always an element having a multiplicative inverse, other than that, this ring doesn't have other multiplicative inverses. So it is not a field either. In conclusion, among the 3 examples of rings we considered, only one of them was a field. Real numbers with usual multiplication and addition. Other examples of fields include complex numbers, where again we take usual multiplication and addition, and also integers modulo n, where n is a prime number. One last time, what is a ring? A ring is a mathematical structure consisting of a set R equipped with 2 binary operations, multiplication and addition, such that addition gives an abelian group structure on R, multiplication gives a monoid structure on R, which doesn't have to be necessarily commutative, although in a field it does have to be, but not in a ring. When multiplication is commutative, we call it a commutative ring. But anyhow, we just require this to be a monoid structure, only associativity and existence of identity element. And finally, the multiplication is to distribute over addition both from left and from right. That's what a ring is.